So in this video, we're going to take a look at how batteries work. This topic isn't explicitly on the AP Physics curriculum for AP Physics exam, but it's actually more on the AP Chemistry exam. But I find that to understand what's going on in a circuit and how the circuit is doing what it's doing, it really does help to have a little bit of an understanding of what's going on inside a battery. So here we go. So I like to call this the tale of two Italians, is how I'm going to start. And it's going to be talking about these two fellows, Alessandro Volta and Luigi Galvani. These fellows lived and did their work in the 18th century. And the story here today actually comes from the 1780s, which would be about the same time as just after the American Revolution. So Luigi Galvani is this scientist in Italy, and he's interested in living things and how they work. And so he's been doing some experiments with frogs. And in his experiments, he's using an electrostatic generator, like kind of like a Van de Graaff generator. You've got a part that turns, that rubs two different materials together. And as those parts rub against each other, they build up a static electric charge. And so it's like, hand cranking this thing. And so he's found that if he goes ahead and he uses the generator to run some electric charge into dead frog's legs, that it will go ahead and it will make the legs twitch. Okay, so he's the person who actually discovers that electrical charge is what makes muscle contractions work.
As a scientific celebrity and professor of experimental physics at the University of Pavia, at the age of 46, Volta might have rested on his well-deserved laurels. However, Volta happened to receive a timely letter from one Luigi Galvani. Galvani lived in Bologna, and like Volta, he was an Italian given to bold ideas and shocking discoveries. Perhaps the boldest and most shocking was an idea Galvani called animal electricity. This was a vital force, wrote Galvani, different from ordinary electricity, and it could be found in the tissue of a frog. Then as now, an electric impulse causes a frog's leg to twitch. In other words, when the thigh nerve of a freshly dissected frog is given a small electric impulse, a muscle contraction occurs. By observing the twitching of a severed frog's leg, Galvani had discovered that those nerve impulses which excite muscles into action are really electrical signals.
One day he's doing his experiment with his frogs, right? Quick little sketch here. Hey, look, here's one of Galvani's frogs. So let's see. There's like a lower leg. Here's a big fat frog thigh, right? Another frog leg, right? Big fat frog thigh. Here, webbed feet, right? Froggy feet, right? Okay, and his frog kind of stops kind of abruptly here because he's gone ahead and it's dissected, right? So this is this frog that he's just worked with, and here is the frog's spinal column, and look, there's a little froggy brain. All right, and so what Galvani's doing is he's doing his little experiments and poking around through the different tissues in the frog, right? And to do this, perhaps he's using some probes, and like one of his metal probes that he's poking around with here is made out of brass, right? Made out of that metal. And when he's kind of done toying around with this frog that's, sitting in this kind of puddle of, frog juice and salt water, and he goes ahead and, happens to lean that little brass, probe up against this iron rail there, right? And when he does that, all of a sudden, the dead frog's leg twitches, right? Now, keep in mind that it's not hooked up to electrostatic generator at all at this point, right? And just all of a sudden, the dead frog's leg twitches. Well, this, of course, gets Galvani all excited, right? He's like, well, gosh, where's this electricity coming from, right? And he says, oh, it must be somehow in the frog, coming from the frog itself. There must have been some electricity stored up in the tissues of the frog, right? And perhaps this energy, he calls it like animal electricity, is actually, maybe this is like the life force itself that makes living things work, right? And he gets all excited about this. And so, of course, he then writes to all the other scientists in his acquaintance about his big discovery of animal electricity. Well, one of the people who gets these letters from Galvani is Alessandro Volta. And Volta is kind of Europe's leading expert on electricity, kind of like Ben Franklin's America's expert on electricity. Volta is Europe's. Volta, do you remember the lab we did where we took fur and cloth and wool and stuff, and we rubbed them on like big sheets of pink foam insulation, and it charged up? And then we went ahead and took a metal pan and brought it nearby and touched the pan, and that charged the pan up. Do you remember that? The person who first did that and developed a device like that was Alessandro Volta. Okay, he called it the electrophorus or electric bearer. But anyway, he could use it to carry electric charge around. But anyway, when he gets Galvani's letter, he says, I don't think that means what you think it means. I don't think that this electricity is coming from the frog. He says, I think that electricity is coming just from the fact that you took two different metals and put them into contact.
Alessandro Volta came along before anyone was able to construct an electric battery, much less see the inner workings of a metal. But Volta did have a knowledge of metals, their properties, and how they work. And in that regard, Alessandro Volta was considerably ahead of his time.
Contact. So let's explain what Volta's saying. And so it kind of goes like this. You'll recall that if I have different metals, right? Now, brass is actually a combination of what? Copper and zinc, right? So let's just pick as our examples. I'm going to pick two different metals, if that's okay, if I'm not using the one specifically from this experiment. So say I've got two samples of metal, all right? And say one of these metals we'll say is silver, okay? And then I have a sample of another metal, right? And for my purposes, I'm going to use zinc because that's what Volta used. Now, you say zinc atoms and silver atoms, they're different from each other, right? They got different numbers of protons and neutrons and electrons. And where this becomes important is when we start talking about electric potential, right? Electric potential, this big V guy, right? You say, oftentimes we call this thing voltage, right? And you say, hey, voltage, Volta, you say, yeah, it's named after this guy. Voltage, remember we said that's the electric potential energy per charge at a location. So we say, hey, for every coulomb of charge that I put here, there'll be this many joules of electric potential energy stored up at that location for that arrangement of charges, right? We said, hey, V is a value of a location. So maybe we say, hey, right there, hey, I want to know what the V value is there. And you say, hey, for every positive charge in the area, it's going to increase the electric potential, increase the V value there. Put more positive charge in the area, the V value there goes up, up, up. Put some negative charges around the area, V value goes down, down, down. And so the configuration, the arrangement of these charges determines the V value. And you say, hey, if I looked at a location infinitely far away from the charges, the V would be 0. And as I get closer to positives, the V goes up, closer to negatives, V goes down. Good enough. Well, different metals have different arrangements of charges in them, don't they? And so wouldn't it make sense that the V value at the surface or at the outer layer, say the valence level of a silver atom, would be a different V level than the valence level on the outside of a zinc atom? So what that means is if I've got a certain V value on the outside of silver atoms and a certain V value over here on the outside of the zinc atoms in that sample of zinc, there would be a delta V between them. And you say, oh, yeah, delta V. You say, if I've got a delta V, you say that means there is a change in electric potential energy per charge, right? Between two locations, location on a silver atom, location on a zinc atom. You say, all right. Well, if there's a delta V, that means there's a change in potential energy going from one spot to the other. You say, wait, I remember that all potential energies, they always have some sort of a force that's associated with them. In this case, it's the electric force, which means there must be an electric force to push against, with or against going between those locations if there's a delta V. In other words, if I look at this formula, potential difference is negative integral E dot dr, that path integral going from like one position to the other position. You say, if there's a delta V between those two locations, that means when I do this integral and I do this dot product, taking my dot product of the E field with this little path as I go along each little bit of the path, you say there must be a component of E field parallel to that path, right? If I'm going to have a delta V. If there's a delta V between silver and zinc, then that means I must set up an E field between these guys, right? And this E field, right, here from the high potential to low potential, silver is going to be a location of higher potential, and zinc is location of low V or low potential, right? And you say what's going to happen then is electrons will get pushed tend to get pushed from the zinc to the silver. Do you remember that at locations of low V, this is where a negative charge would have high electric potential energy. In a location with high V, that's where a negative charge would have low electric potential energy. It's like everything's kind of backwards for an electron. And my E field goes from high V to low V always. So the point is, electrons would tend, if I go ahead and I put two metals together, then electrons would tend to get yanked from the zinc, would head towards the silver, right? By that E field between them. And you say, oh, okay. And so Volta is saying, hey, when I have these two different metals here, right, in Galvani's experiment with the frog, you say, hey, when I put those in contact, that's going to make charges want to flow from the, I don't know, either the zinc to the brass, from the copper and zinc and the brass to the iron, or from the iron to the copper and zinc to the brass. It doesn't really matter for us which way it flows. The point is, it's going to make some current flow, and that's going to trigger the nerves to trigger the frog's leg muscles to contract and make the frog's legs twitch. And so he's saying it's because there's two metals, this energy is not coming from the frog, it's from this difference in potential between the two metals. So Volta wants to make this very clear, that the energy is not coming from something organic. It's not this animal electricity. It's just a change in potential between two metals. And so to do that, he has to set up a little demonstration of this using something inorganic, using just some samples of these metals. So here's the way that works. So you say, well, can I just take some silver and some zinc and put them in contact and show that? And you say, well, gosh, if I just touch those two bits of metal together, what's going to happen is this. You say some electrons would get yanked, right, out of the zinc, right, and would head over into the silver atoms, right? Okay, they'll go from low V to high V. That's the way the electrons go. They go uphill, right? And so you say, well, if electrons head over there, what's that going to do to this metal? You say, well, if I start putting electrons into here, right, as I put more negative charges here, what does that do to the V value here? Well, that V value will go down as I add more negative charges in that area. Well, as the negatives leave here, that means this region over here in the zinc is going to start to charge up more positively, won't it? You see, if I make this more positive, what happens to the V level over here on the zinc? Well, that V level would go up. And so what happens to the change in V? I had high V on the left side, low V on the right side. Well, now the high V got lower and the low V got higher. The delta V gets smaller, smaller, smaller. When the delta V gets to zero, right, when those two V's are the same, you say, come over here, you say, gosh, that delta V goes to zero. Well, that means that E field between them then goes to zero. There's no force in the charge, and the charges stop flowing. Looked at another way, as I start putting more negatives over here on the silver, that's going to repel more electrons from coming in. So this charge isn't going to flow forever. In fact, if you go and you touch the two metals together, the charge will flow over just like that in an instant, and then it's done. And you say, well, that's not very useful, and that's not really hard for people to see what's going on. So here's the clever idea that Volta has. What he does is he says, well, you know, if I want to keep that charge flowing, right, for a longer period of time, then what I can do is take my two samples of metal, right? Take my silver, take my zinc, And I'm going to go ahead and separate them a little bit here. There's two samples, two metals, right? And so here's my silver, right? And here's my zinc. And say I want to touch them together. What I'm doing is I'm just going to connect them by a little wire, okay, connecting across. And you say, okay, once again, at the low V side is over here. So my electrons, once I make this connection, the electrons would want to flow this way. But as that happens, the zinc would start to lose electrons, so it would become charged up positively. And then the electrons don't really want to leave anymore. And over here, the silver is charged up negatively, and the electrons don't really want to go there anymore, and it kind of stops. So Volta's amazingly clever idea. Okay, and I don't know if this was inspired by thinking about what's happening with the frog and the liquid here, or if this is something that Volta had already figured out on his own, possibly. But what he says is, you know what I'm going to do? I'm going to take my two samples of metal. I'm going to put them in a container here, right? Stick them in this container that I've got some liquid in, right? All right, so there's some liquid in here, right? And so in this water then, right, he's going to go ahead and dissolve in some ions, right? And so you say, I'm going to put in here something that breaks up into a lot of ions. Now, you might remember from chem class that a compound that you put in water and it breaks apart and makes lots of ions, we call things like that salts, right? But so you have all these like positive and negative charges. And other things you can use besides just like ionic compounds that break apart into lots of ions, you can use, you know what else makes lots of ions in water? Solutions of acids or bases, right? Acids we think of those sometimes as being things that produce hydrogen ions. And those hydrogens are going to grab onto the waters, make hydroniums, H3O pluses, right? Or put some base in there. And base is something that's going to grab protons off the water and turn it into OH minus hydroxide ions. So the point is I'm going to have these ions in the water, whether I'm doing it with a salt or doing that with an acid or a base. But the point is, here's what's going to happen once I've done this. You say, these electrons leave, right? And they're going here from where they have high electric potential energy at the low V side of the side here. They're going to move over here to the high V side, right, where they have less potential energy. As they go over, they're losing potential energy, gaining kinetic. That's how they move, right? Okay, there's an E field actually set up in the wire that pushes them across. And you say, now wait a minute. I thought that in a conductor, right, in these metals, shouldn't there be no E field? You said, I thought the E field was zero in a conductor. That's just the case for a conductor that's in equilibrium. What happens is, if I set up this voltage here, electrons will move from one side to the other until the total force on the electrons goes to zero, and they move to balance that out so that there's no E field inside. And that takes, like I said, just a fraction of a second until we immerse them in this ionic solution. So here's what happens. You say, do you remember that if I go ahead and I stick a bar of zinc in some water, is that zinc going to dissolve? You say, no. Neutral zinc doesn't dissolve. But if I have ions, right, if I pop some electrons off the zinc atoms, I can make zinc ions, little positive ions, and then they can dissolve into the water. You remember that water is this polar molecule, and like a polar solvent, you said it can dissolve ionic things. That's that whole like dissolves like business. And so what will happen then is either these positive ions will pop off in a solution or some negative ions can come over and neutralize them out. So what that's going to do is that's going to keep this nice and neutral, right, as these positive ions pop off into solution. Over here on the silver, we have these electrons heading over there, charging that up negatively, which would kind of keep more electrons from going in eventually. But once I have it in this solution, what will happen is positive ions in solution can drift over here, right, attract to this negative, and then they'll go ahead and neutralize out that negative charge, right? And so this chunk that was a positive ion, if it becomes neutral, well, now it's not going to dissolve in the water. Oftentimes it might kind of plate out there, right? And I'll get this ion, then this thing that was an ion now stuck, this neutral atom stuck onto that silver. And so I can go ahead and I can start plating out, right? Maybe I have silver ions here in the water, they'll then stick on very nicely onto the silver bar. And so what's happening then, when those positive ions come over and they attract here and they stick on, they neutralize out these electrons, right, that were moving over to the silver bar. And so now I'm keeping that bar of silver nice and neutral. And I'm keeping my zinc bar nice and neutral. And so what that means is I'm going to keep that nice delta V there, stays the same. I'm not going to have this buildup of charges, and so electrons will keep moving from where they have lots of potential energy on the zinc to where they have less potential energy on the silver. And those electrons just keep flowing, right? And now I have this nice current, this nice flow of charge that I can use to do things, right? And the trick is using this electrolytic solution, the solution that has these ions in it, to help keep these the two metal bars here, we'll call them electrodes, to keep those electrodes neutral. Okay, and so this setup is called an electrochemical cell. Okay, we call the two metals, or the two conductors, I should say, that we put in there. We go ahead and we call these the electrodes. The one that is the low V one is called the anode, and the high V one is called the cathode. That's not important that you know that. Electrochemical cells are sometimes called galvanic cells, after Galvani. But that's the deal. So I have, what this does is it creates a delta V, then the delta V between the two metals. And because we keep those, keep charge from building up on these, the electrons want to keep flowing from low V to high V, and we keep this current flowing and keep that delta V constant, ideally. And so that's it. That's this trick, right? When Volta wants to go ahead and show this to Galvani, he creates this kind of model of this. He kind of sets up where he's going to take plates, little like discs of metal, of the different metals, right? So like here's some discs of say zinc, right? And he takes a whole big, huge stack of tons of these little plates, right? And these are zinc. And then he's got stacked up his plates in between there. Then he's going to have plates that are silver, right? Right. And then if you just, touch them together, the charges flow and it's done. So in between them, then he goes ahead and he inserts in between there a little bit of, he takes like some, kind of paper or some cloth or fabric, or even like, animal skin or whatever, takes stuff that he then soaks in ionic solution and puts that damp stuff in between these guys so the ions can flow right between them, right? And you go ahead, take this guy, go ahead, connect, say wire out the top, wire out the bottom, right? And when you make the connection, electrons will go ahead and kind of flow right on out here, right? And I'll get electrons flowing around. Okay, and this is the world's first battery. Okay, Volta makes this thing. It was this pile of alternating different metal plates with, again, those material that's soaked in electrolytic solution between them, making current flow. Where for the first time you can have a nice steady flow of current, which then enables all these other electrical discoveries to be made. Like I said, this pile of these plates is called the voltaic pile, after Volta, the world's first battery. Now, understanding this, how this works, kind of gives you some insights then about what batteries do and how they do what they do. Check this out. Say I've got my two electrodes here, right? I've got my zinc electrode and my silver electrode, right? And electrons are going to flow out of the zinc, leaving behind positive ions. But these positive ions will then pop off into solution, right? Over time, right, as these positive ions are popping off, what's going to happen to that zinc terminal, that zinc electrode? You say, well, isn't that zinc going to kind of wear away? Yeah. And as it's oxidizing here, it'll kind of get all this kind of oxidation on and stuff, and it'll slowly kind of get eaten away over time. What do you suppose happens when all that terminal is eaten away? What do you suppose happens to this battery? Well, then the battery is dead, right? Okay, when it runs out of zinc. Okay, and that's how batteries go dead. Okay. The other thing that's interesting about this, for me, is you say, hey, if I went ahead and I cut open a battery, and I have a battery at school like this that I ran for a long time and used, and then cut open so you could see the insides. I have a few batteries like that. But what you'll notice is that the zinc electrode is all like eaten away like this. Well, we're going to do in this unit these special diagrams for analyzing circuits called circuit diagrams. And we'll have symbols to represent the different things in the circuit. The symbol for a battery, right? The circuit symbol for battery, it looks like this. Look, here's a wire coming in. And then look, here's the two electrodes. One of them is long, one of them is short, wire going out. You say, hey, that long one, that is kind of like the silver electrode here. You say that long one, that's the high potential side, the high V side of the battery, right? We usually put a little plus by it. And then the other end, that's the low V side of the battery, and that's the side that's getting eaten away. That's the side that's going to be shorter, and that's the short line, right? We usually label that one with a little negative. Now, when we do that, we're saying plus and minus there. That's just to represent high V and low V. Remember, the whole trick of the battery is we're keeping these two electrodes neutral, right? Okay, they're not actually charged up positively and negatively, but it's just showing high V and low V is what that plus and minus is meant to indicate, not charge. But that's the symbol, and I think that's why it's that symbol, is because that's what actually happens to the electrodes there. Second thing, as a side note, is you say, well, gosh, if these positive ions in solution are coming over here and they're going to stick on as they grab the electrons off the silver, and they'll neutralize out, so now they're not going to dissolve anymore in the water. They'll go ahead, they can get them to plate out here. This is kind of like how we electroplate things, put a metal coating on things. We're not dipping them in molten metal typically. What we're doing is we're electroplating them like this. And so that's how that gets done. If I have a rechargeable battery, right? How do I recharge a battery? Well, I need to make this little chemical reaction go in reverse, don't I? I need to make, what I'm going to do is I'm going to take the electrons and I'm going to push them from here on the left side where they're at high potential on the silver. I need to push them backwards, right? Push my little electrons the other way and we'll move over here. As they do that, as electrons leave, this would become positive. Positive ions will pop back off into solution. As the electrons come over here to the zinc side, you say positive ions from solution would then come on over and plate out here on the zinc, and you'd rebuild that electrode. And so that's the idea, is say, well, to do that, I have to move electrons from where they have low potential energy on the silver to where they have high potential energy on the zinc, which means I have to pump energy into the system to push those electrons to where they have more potential energy. And so that's what's going on when you recharge a battery. While we're on it, the term battery, I told you that this setup here, one electrode, one cathode, one anode, two electrodes here in the solution, we called this a electrochemical cell, right? Okay, well, prepare yourself for what seems like a non sequitur. I don't know how much military theory you've read or talked about tactics and stuff, but really briefly, I want to talk about artillery. Artillery, you say, like for example, like say cannons, right? So I got my cannon wheel there and my cannon set up, right? Yeah, okay. And I have some cannons, right? I'm gonna go ahead and we're gonna that's terrible. That's awful. Anyway, the point is, get into this. The cannons get smaller as we go down. Anyway, over here, here's the enemy troops, right, marching along. You say now, cannons, they're used. Artillery is used for siege and knocking holes in walls and stuff. But on the main battlefield, it's meant for like shooting at enemy troops to try to get them to not come over and kill you. And so what they discovered is that if I have some artillery pieces, if I go ahead and I fire a cannonball, dunk, 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 right? And, so much for that guy, right? You say the rest of the formation here marching up, they're like, stinks to be that guy, right? And they keep on coming over to kill you. If you fire your cannons like kind of one at a time here, and boom, that guy does like, oh, okay, whatever, sucks to be him, right? And they keep coming on. What they found is if they grouped their artillery together and had them all fire together at units, and a fourth of the guys fall down dead, everyone else is like, well, I'm out of here, and they take off running, right? And so it's more effective to group your artillery together. When they group artillery together like this, they call this an artillery battery. And so that's where this term is coming from. When you take electrochemical cells and you put them together, and multiple of them, then you make an electrical battery. Now, this delta V that we're creating in a battery, that's its purpose, is to make a delta V, a potential difference, to make charges flow in the wire. And you say, when I do this, I'm going to create a delta V by having two different conductors, right? In this case, we're using silver and zinc. In most batteries, like the batteries I grew up with, those batteries inside the two terminals, one of them would actually be made out of carbon, and then the other one would be made out of zinc. Okay, I'm not going to bother drawing it the way it really is in a battery, the way they arrange it, but we have carbon and zinc. You say, no, wait, carbon, wait, we're supposed to have two conductors here in my battery. Is carbon a conductor? Well, you might remember that even though carbon is a non-metal, right, remember that it comes in different forms, different allotropes. You can have graphite, or you can have diamond, or you can have fullerene. Well, it turns out that even though carbon is a nonmetal, when you arrange it in the patterns of graphite or fullerene, it actually provides a way that electrons can flow from carbon atom to carbon atom to carbon atom, kind of between these sheets of carbons. And so they actually are good conductors, it turns out. And so carbon is a lot cheaper than a metal to produce, and so they make one terminal out of carbon. So anyway, but the point is, the delta V, the change in potential between carbon atoms and zinc atoms, is actually about 1.5 volts. And so I don't know if you've ever looked at batteries at your little batteries and read on the side of the battery, you'll notice that on the battery it says it's 1.5 volts for like a little AA battery, right? Like used in a lot of devices, or AAA batteries go in your calculators, right? Or big C cells or D cells like we put in the constant velocity buggies we played around with last year. But the point is, these batteries, they're different sizes, but they're all really the same two materials inside, and so they're 1.5 volt batteries. The different sizes are just so that they can fit in different devices, and so that it will take longer to wear down all that zinc, right? The battery will last longer. Now, there's some other batteries out there. For example, there's these rectangular ones, right, that you've seen, right, that look like this, right? And remember what you called it, and the ones that they got the little terminal looks like that, and the terminal looks like that, right? You remember what these are called, right? These are called 9-volt batteries. You say, I wonder why they're 9 volts. Well, if you were to break them open, you'd find that they're made out of carbon and zinc. And you say, well, yeah, shouldn't that be 1.5 volts? Well, you know why it's 9 volts? Because inside there are 6 electrochemical cells wired up in series. And so together they make 9 volts, 6 times 1.5, 9 volts, right? There's also these great big, huge lantern batteries, they're called, right? And they got kind of these, like, usually kind of spring attachments, right? High V, low V terminals, right? High V, low V, right? And you say, well, those on the side, they'll tell you that they are 6 volts. And if you broke it open, these big, huge lantern batteries, inside you'd find there were 4 electrochemical cells. And you say, no, why is it so big? Well, that's just so that it takes a long time for the charge to wear away the zinc electrodes. And so you say, so that's the idea. So again, for these batteries, they're all like 1.5 volt delta V between the two conductors in them, and that's how that works. So what do I want you to take away from this? Here is kind of the takeaway from this. We recognize that what's happening in a battery, in a circuit, is I've got 2 different conductors. There is a delta V between them, which means it will set up an E field in the circuit. The E field will run preferentially through the metal, actually, the E field lines, to push electrons around inside my circuit. And so that's the first thing I want you to recognize, is that the battery's job is to make a delta V, to provide energy for the charges to flow. So running through, turns out there are 3, and there's a couple things we're going to get from this. So it turns out there are 3 requirements for a DC circuit. For an electric circuit. Okay. The first requirement is you need a source of delta V, of potential difference, right? This is typically going to be a battery, like we just talked about today. You can use a generator. There's from biology class, hopefully, that at the teeny tiny level, in, like, say, for example, plant cells, they go ahead and they use photosynthesis. And when they do that, part of it is pushing electrons around from thing to thing. Yeah. Okay. When that's being powered by energy from sunlight, you can have piezoelectricity where you apply pressure to certain crystals and that pushes electrons around. But anyway, but typically battery generator we're going to talk about for this course. Battery is what we're dealing with this unit. And you say, why do we need a source of delta V? Because it provides energy, right, for the charges to flow. Again, we know that if I have a delta V, I have a change in electric potential energy between those two locations for those charges to move. Give the charges energy to move. The second thing that we need, right, which I hope makes more sense now, is we need a complete loop of conductor. Let me show you what I'm talking about. In my battery here, we know that up top, I'm going to have negative charges, electrons flowing from the low V terminal, the low V electrode to the high V electrode, right? So I've got negatives flowing this way, right? You say, well, they come over here, but then what happens here in the solution then? What I have is I have positive ions essentially drifting this way, don't I? You say, no, wait a minute. Negatives coming around this way, and have a negative going to the right. Charge-wise, isn't that basically the same, a similar sort of thing to having a positive going left? The left side here is going to becoming raising potential. Becoming more positive, right? Same thing as if an electron had moved to the right, it would be the silver would become more positive. The electron had left it. A positive coming in, just the same sort of thing, makes it more positive, makes the zinc more negative. And so essentially, I have charge flowing around in a loop. Okay, makes sense. And so I have this complete loop for charge to flow around. Why is that important? Well, what would happen if I didn't have this electrolytic solution here? Well, electrons would flow over, and then electrons would build up, and then no more electrons would want to go there, right? Yeah. And so that charge building up over here would prevent more charge from flowing, and the current would stop. The charge would stop flowing, right? Same thing here. This would become more positive, and then electrons would want to leave. You say, but by having this complete path, charges keep flowing around, and we're taking energy that was stored up, electric potential energy in the arrangement of the atoms in the zinc, and change between that and the arrangement of the atoms in the silver. And you say that's losing potential energy and gaining connected. Let's move. You say, but I need to have that complete path to keep charge from building up anywhere and blocking the flow. What's happening is if I have a metal, right, and I have an E field set up in the metal, electrons are free to move, and they will move until they balance out. They build up and balance out that force from the E field that made them move, and they make an E field themselves that cancels it out. You say, but what we're doing here is those electrons are trying to move to get to electrostatic equilibrium. But what we're doing is we're pulling the rug out from under them. Those electrons are moving over, right? And they're saying, oh, there's this E field shoving me along. I'm going to put more and more electrons over here to make an E field to fight against that, right? To kind of balance it out. You say, but every time they try to build up charge, we neutralize them out. We keep pulling the rug out from under them, and so they can never get to equilibrium, and the charge just keeps flowing. That's the trick of how this works. And so we said, hey, a circuit needs to have a complete loop of conductor. And you say, hey, why does it need this? To keep everything neutral. Okay, so charge doesn't build up and resist the flow. Charge doesn't build up and stop the flow. All right. The third thing that every circuit needs, okay, is not quite so obvious here. One more thing, complete loop of conductor. You'll recall, right? Something we talked about last unit was we talked about capacitors, right? Now, capacitors, the circuit symbol is two lines of equal length, right? Those are two metal plates of a capacitor. We said, hey, if I hook this up to a battery or whatever, right? Okay. You said, hey, my electrons would start to flow around. And you say, what's going to happen here? Electrons would start to flow this way. I start getting electrons built up on this plate and positive charges built up on this plate as electrons are drawn off it. But you say, but eventually then that charge will stop. I can't pull any more electrons off this. This becomes more positive, and I can't push more electrons in this plate as this becomes more negative, and the current stops, right? And it takes We'll talk more about how that works next week when we go into more complicated RC circuits. It's the last topic for the AP exam this year. And so you say, well, gosh, again, in a capacitor, when the capacitor gets fully charged, it is going to stop the flow of charge in that circuit. And I won't have and so basically that whatever branch in the circuit that capacitor in it will go dead and no more charge will flow in it. But anyway, but getting back to this. So the third thing that we said that every circuit needs that's going to be having current flowing through is it needs something that we call resistance. Every circuit is going to have that's charge flowing in it is going to have some resistance. Why? What does that do for us? Well, what resistance is, it's something that takes the energy back out of the charges, right? So to remove energy from the charges that are flowing. So if you think about it, I set this circuit up, right? And we say, hey, we've got these electrons that are flowing over. You say, as they go from the low V terminal where they have high potential energy to the high V terminal where they high V electrode where they have low potential energy, they're losing electric potential energy that's giving them kinetic to move. But then where does that energy go then once they get over here? You say, what we typically do is in here in this wire, this is where we'll set up some device that we want to be powering with this, okay? Now, that could be a skinny little filament of wire that's so really skinny it's going to get really hot and it's going to heat it up, and that's where the energy is going to go to heating up that wire. Maybe it's like coils we want to heat up to like cook our toast in a toaster, right? Or maybe it's a little skinny filament of wire that's going to get really hot, so hot that it glows in an incandescent light bulb. Or maybe it's coils in an electric motor, right? We're gonna take that energy, that electrical energy, and turn it into kinetic energy, pushing, driving that motor to turn things or move things. But the point is, we're going to take energy out. This part that takes energy out, sometimes it's called the load of the circuit, but we'll be taking energy out through resistance. Okay, so pretty much every circuit is going to have resistance. Take the energy back out of the charges. Right. Otherwise, what would happen? Electrons would come over here with like energy, just get electrons getting more and more and more energy. That doesn't make sense. If I tried to make a circuit without anything, trying not to have any resistance here, right, as little as I can, maybe I just connect like one wire straight across the two terminals of the battery. I don't know if you've ever tried that. It's not a good idea. If I just connect across from one side to the other side of the battery, what'll happen is, the wire will start to get hot. We'll talk more about this. If I connect just a wire across, the charges would just kind of flow around, right, through the battery, through the liquid there. But what'll happen is, it turns out the materials of the battery themselves have some resistance. And so the battery will start taking energy out in the form of heat. And so this will start getting hot. Well, you remember that between the terminals of the battery, we have this kind of goop, this kind of moist goop in there. Well, when I heat that up, what might happen to the liquid in that? Well, if it gets hot enough, it could vaporize. And when it vaporizes, it expands and you can burst the battery and stuff, which, has these chemicals in it that's not real great for you to be messing around with, perhaps. And so you say, so you don't want to do that. It's called short-circuiting the battery, and we'll talk more about that. But that's the idea, is that you say there's always going to be some resistance. There's resistance in the battery itself, and that is a topic for talk about quickly another day. Small little topic. So that's it. So that's the main stuff that I want you to get out of this. It kind of explains a little bit about circuits and why when you cut the wire, the circuit stops working. It's because charge builds up now and prevents more charge from flowing. And you say, and I understand why I need a battery. It's giving the electrons energy to flow. You understand about being made of different materials and how it generates a delta V. Okay, and that is the purpose of a battery. For our purposes, we will generally be using what we call ideal batteries. Okay, in all of our calculations, you say, hey, an ideal battery. What makes an ideal battery is it maintains a constant delta V. Okay, that's what makes that's the battery's job, and we'll consider that delta V to be constant. In real life, does the delta V from one side to the other side of the battery remain constant the whole time? No, and that's something we will talk about in the next 2 weeks, briefly about kind of open circuit and closed circuit voltage, we call it. We'll talk about that. As batteries kind of wear down and corrode, the materials get kind of gunked up and stuff gets in there, and the V value changes a little bit. But we will consider for our calculation delta V from a battery to be constant. Okay, that's it for this video. From here, we'll move on to talking a little bit more about the basics of circuits and how they work, and start doing the simplest calculations with DC circuits.